Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so it's my great pleasure to introduce Francesco Lagoso. He's the king of abstract interpretation over in Redmond, and I've been trying to get him to come here for a couple of years now, and for some reason he wanted to visit this week. So over to you, Francesco.
Okay, thank you. So thank you for hosting me. It's a very nice visit, and I'm going to talk some work I did with my colleagues in Microsoft Research in Redmond, and with Manuel Fendrich, Mike Barnett, Tom Ball, and Shuvendo Lahiri, and Manuel now moved to Google, and with some interns, and I think probably you know some of them. It was not me who called them interns. They auto-defined themselves my interns, so it was kind of, they are good interns, you know. So I recommend you. So okay, you know what I like, what I'm passionate about, but actually there is something I'm even more passionate about. It's incredible to say. Sorry? Yeah. So it's usable verification. It's to bring verification to the working programmer, make verification part of the everyday activity of every programmer. So my dream is to have verification as easy to use as today is easy to use a compiler or to use unit testing. Now, what we need in order to accomplish this dream? Well, first we need a practical specification language, a language which a programmer can use without having a PhD in computer science or in maths or in logic. And then we need tools. We need tools that really helps the programmer, not that are helped by the programmer. So the tools, they really should provide some feedback that should be useful for the programmer. So in these tools, they should have a minimal change to the building environment, because otherwise, you know, they will not be adopted. They should be as automatic as possible. They should do as much inference as possible, and they should scale up, because programs out there are very large, are tens of thousands of classes. There are hundreds of thousands, if not millions of lines of code, and they contain hundreds of projects. So this thing really should go on the scale. Now, what is the first step for verifying? Well, the first step for verifying is having a specification. It's writing a specification, something, you know, say what your program does. And the first question is, do programmers write specification nowadays? And the answer is yes, at least for .NET. What's, you know, programmers I'm interested in. Programmers in .NET today, they write parameter validation, which you can think as precondition. If they do WPF, they write data contracts, and then they have all the kind of attributes used by all kind of tools out there. So yes, they write specification. What we want is to have them to write more expressive specification, in particular as contracts and contracts. Well, you know, are just precondition, postcondition, and object invariants. Now, how do we do it? The usual way is to say, okay, now change a language, provide a language which has some support for contracts. So example are Eiffel, Spec Sharp, or JML. Now, this is very nice solution because you get nice syntax and you get many of the features, you know, integrating the IDE. It's very nice. But the problem is that for those approaches, they require too much changes that programmers, they are not ready to go. One main change is to change the language. So it's difficult to switch them from C# to Eiffel, for instance. And the other one, for instance, is the changing of compiler. They don't trust academic compilers. They trust, say, Java-C or CSC.exe. So our pragmatic solution is say, okay, if you want to extend the language, let's do how they usually do in managed Word. You just provide a library in which you extend the language. In particular, use code in order to specify code. And for those who don't know CodeContracts, that's what a CodeContract specification looks like. So probably you saw this example yesterday in another talk. It's the maximum example. We want to specify a bunch of things about this routine. We want to say that, yeah, it computes the maximum on an array, which we know it's not null, and yes, at least one element. So the way in which we do is just we have this library, which is part of the main library in .NET, in MS Core Lib, which method call is essentially it's a placemaker. It's a marker for preconditions, postcondition, and then we have also some API for specifying a for all and exist. And we have some special method in order to talk about the result value, because in C# or in mainstream languages, you don't have any syntax in order to talk about the value returned by the method. So we use this one as a marker. So the nice thing about doing it is that we don't need to change anything in C#. This is just a method call. Compiler knows how to produce a method call, and we are happy. Now you may ask, OK, so first, why you need contracts at all? We already have the bug.assert. That's one of the classical questions. Well, the problem with asserts are that those are not visible to the caller. They don't really work well with object-oriented programming because those cannot be inherited. You cannot put assert in interface methods. You cannot put asserts in virtual methods and other things. So we have solution. In abstract methods. We have solution for that, but I will not talk about it today. Sorry. Then the next thing is say, oh, but you can use attributes. You have no-null. You can put no-null attributes and this kind of stuff. The problem with attributes is that they are not really expressive. There's very little things you have to express. If you want to express something, you have to serialize as a string. So it becomes a kind of nightmare and not readable. And some people in University of Washington, they came out with attributes for specifying non-nullness in Java. And they came out, I think you have 17 or 19 different attributes in order to specify meaningful things in Java. So you see, it's kind of a burden to a programmer. And the third thing is why you don't use comments, as for instance, I do JML. Well, the problem with comments is that those are completely ignored by the compiler. So you have no type checking, you have no syntax highlighting, you don't have any code generation from the compiler. So that's why we went with this solution of using CodeContracts, of using code in order to specify code. And the thing about this solution is that it's very, very pragmatic. We don't need a new language. We don't need a new compiler. We can leverage all the type checking, all the code generation the compiler does. We have all the nice syntax highlighting and all like this. So it's beautiful. People have been downloading it, 100,000 downloads so far, 70,000 just in 1 year and a half. So people, they wrote blogs and book chapters about it, and it's used inside outside the company. So all this is wonderful, except that, well, we lost beauty. It's not so beauty. I'm the first to admit that probably this thing, okay, it's not really very, very beautiful, but it's pragmatic. That's some trade-off. And well, once you have a way of writing contracts, you want to do something with it. Well, you can generate documentation. I will not talk about it today. Or you can do runtime checking and static checking. And I just tell that runtime checking, we do it by doing some binary rewriting. And again, I'm not talking about it today because I talk about what I'm really, really passionate, which is static verification. So we want to prove our specification. We want to prove our contracts. We want to prove that our program does not have buffer overrun. It does not have null pointer checker, division by zero, and other things. So I've been developing with Manuel. This tool is called the Clousot. I guess it's you know why, because of the famous inspector Clousot, or because also it's based on abstract interpretation. So it's more or less this game. And how it works. This is a high-level view of the tool. What it does is it takes as input an assembly and constructs a call-for graph. And then it starts visiting call-for graph bottom-up. And for each method I analyze, so I construct a control-for graph. Then it adds contracts. So it goes and finds which are the contracts. This can be out-of-band contracts, it can be inherited contracts, contracts in the code. And it inserts them here. So in orange, you see those are asserts. So for instance, at the exit of the method, we wanted to assert the postcondition. And the green one, and before calling some method, you want to assert this precondition. Green ones are the assumes, are the things that you can rely on. So when you enter at the end of the method, you rely on the precondition of the method. And after you call something, you can rely on the postcondition of the method. Once we built this augmented control flow graph, we do abstract interpretation. So we have a bunch of abstract domain. And theoretically, what we do is to infer each program point an invariant in this abstract domain, try to be as precise as possible, that alters this program point. And then we collect all the orange dots. We take our invariant and we see if the invariant implies the soundness, implies the absence, the correctness of the assertion. If this is not the case, then we use another abstract domain, more refined, and we analyze again until we run out of abstract domains. When we are done, we generate a report. And this report contains several things. So it says which assertions are definitely false, It means that no matter what you do, if you reach that program point, it falls. Which assertion they may be false, so which one for which we are unable to prove them, which assertion they are reached, so we know there is no execution reaching this point, and then we may say which one are proven, but usually we avoid saying these things. Also, and I talk later, we try for the assertion which we cannot prove it, we try to say how you have to change your program in order to fix it, so how you can repair your program. And we perform also contract inference because, well, we need to do some inference. We want this thing to scale up, and we don't want to repeat work already done. So we use also a caching mechanism. And our caching as key, a semantic hash, which is computed up starting from this guy. So essentially, we compute an hash of the semantic control flow graph. And this hash is semantic, so it only takes into account the things that matter for the analysis. And then we write into the database the report, and we use next time. And there's something like this. Now, the question is why we are using abstract interpretation. It's not just because it's the most beautiful things in the world, even better than cycling. So why we are using it? Well, in general, when you do this kind of analysis, what you do, you use some form of weakest precondition. So you get some weakest precondition, then you throw to SMT solver, and then you pray. Yeah, we don't want to have the praying stuff. So we want to be first of all deterministic, and we want to be automatic. So for instance, in the very, very simple example before, so if you want and try to verify this with some usual approach with SMT solvers and so forth, we need to provide a loop invariant. And you see that even for this very actually trivial example, because it's just a for loop with one instruction inside, we have to provide a big loop invariant. And this is not going to work. No one is going to write this loop invariant because they are going to say, oh, this is pretty trivial because I already told you the array is not null. I already told you that it has at least one element, does not get modified. And yeah, it's clear that I is between 0 and a.length. Why should I provide it? It's just a for loop. And then the same, the pre and the post, these other two guys, they look a lot as the post condition. So why should I do it? And then what people they would say, okay, the tool is dumb, forget about it. I'm not going to use it. So first one is inference of loop invariants, and also this deterministic aspect, and the fact that we focus on property of interest. We are not saying we are going to verify everything. We don't aim to fully functional correctness. That's clear. We just non-null is still a big problem. Can take it offline, but there are big code bases still have problem with null, non-null, and no type system will not do the work for other reasons I can take offline if you're interested. So we need to get more information. Okay, so this one. So the other thing is also the inference. So if I take exactly the same example before and I comment the precondition and I run the tool, you see that the tool is also able to infer the precondition. So it's going to tell me that well A should be null because otherwise I get an error here. So infer the first precondition. And also infers that A should have at least one element because again, I will get an error. So the tool can infer the precondition for us. And the second one, it's also nice that it can also infer the postcondition for us. So, the usual tricks that people, they do for inferring this invariance in which they take the postcondition, they do some renaming, and they try to verify that actually it's a loop invariant, would not work in this case because I commented the postcondition. However, the tool does a formal analysis and is able to infer that the value that we return is larger than all the others, and that it exists an element in the array which is like that. There is no magic. This is just a paper which I will not talk about today. Sorry. It's this paper in which we explain how to do it. It's Popol 11 paper. So, as a matter of fact, it turns out that Clousot is kind of complex analyzer, and we have many, many abstract domains in it. So we have some basic domains in which we have, for instance, taking care of things as the compilation of the IL and putting from the IL to tree address code, and then recover expression because we need to recover some expression that get chunked out during a compilation in order to make the analysis more precise. We have to do alias analysis, so we have some heap analysis, and actually our analysis, we call it optimistic, you can call it unsound. We make an assumption, it's unsound, yes. We are optimistic, come on. Okay, so the analysis essentially makes a non-aliasing assumption on the inputs. Or another way of saying is we are doing a form of separation logic. We just say, okay, things that came in input, they don't alias. And the reason for that is because we want to give names to this thing. And it's interesting, there are people, there are 2 students, PhD students at ETH that are doing their PhD thesis on falsifying this hypothesis, and it's pretty interesting. So I think there are also ideas for language design in this thing. Seems to work pretty well in practice. So didn't get any bug report actually. Reporting this, it's kind of weird, but anyway, can take off that. Then I have nullness, and then well, on the top of this, all the rest it's sound. So we have numerical domains, and we have plenty of numerical domains because this is very, very important to really get in very quickly relations and ranges about variables in our program. So we designed new abstract domains. We have papers on that and other things. Also, we wanted to reason about the content of the arrays, of collections, and other things. So we design things that can infer simple forms of quantified invariants for all existing, which they actually scale very, very well. Then we also take into account strings, disjunctions, and use and so forth. So you may expect a nice talk on abstract interpretation with a lot of abstract domain, but I'm not going to do it today. But I'll be here all day until tomorrow, so if you want to talk, I'll be happy to talk. Just want to show you what the experience looks like. So the tools are integrated in Visual Studio, and so you enable static analysis by just clicking this checkbox, and then there are a bunch of other things. So you can say, okay, I want to cache results, what I want to try, to check, I think. Then I hit F6, it builds, and then the static analysis runs in background, and it puts the output in the error list in Visual Studio. And it says which assertions are proven. And so in this case, also says, there is something cannot prove. So it just said that there is a precondition which is too weak. Because, okay, this code is correct, but its caller here, what it's doing is taking I, requires I to be greater or equal to 0, allocates the array, so this is not going to cause a problem. But now the array I'm passing here, can be empty because I can pass 0. And so I can violate this precondition. And so that's what the tool is saying. It's saying essentially this program point here, there is a little error with the context. But the little bug here, the squiggle should be actually here. This should be I greater than 0. So it's clear why. Because otherwise I will get an error. If I pass 0, I get a postcondition violation here, a precondition violation here, or a buffer overrun here. So that's the experience that you get. So now everything is wonderful, isn't it? I can be done with my talk now. Actually, no. Real life, it's harder. It's not enough to give warnings. It's not enough just to say, okay, this thing can be violated. So this is a trivial example in which I have off by 1. I just iterate on the array. I want to set everything to 0, and I made my upper bound incorrect. I don't know, probably because I'm a Pascal programmer. I don't know. And so the tool will say, okay, there may be a buffer overrun. So it's this program point here that gives the alarm. Now, is it enough? Well, what we try to do is also to say how to change the program, what you should do. And so the tool also suggests to say, okay, you can fix your code by replacing I small equal and array.length to I dot small and a.length. It's kind of magic, isn't it? Want to repair the program for you. Oh, actually, by the way, in general, there is only one way of fixing the program. There may be several ones. So another one, for instance, something that should hold is that you want the array not to be empty, because if the array is empty, you get an error immediately, because you go here, 0 smaller equal than 0, and that's an error. So there is also a precondition I suggest. So I want to repair the program. Now, what's the idea about the repairs? In general, if you think very abstract view of program analysis, there are 3 components in program analysis. There is the program, the text I want to analyze. There is a specification, which is what I want to do, what the program is supposed to do. And then there is the analysis of the result, that it can be a dynamic or static analysis. It tells you some information about what the program is doing. It can be over approximation if it is a static analysis, and approximation if it is testing. Now, the usual verification problem is that using the information that you infer, check that the program is specification. And usual approach is say, okay, if I cannot do it, let's go with a more refined abstraction. Let's get more information about the analysis of the program. Now, the code repair problem, it's different. You still keep these three things, but now you take as fixed the analysis and the specification. You say, oh, the program, you really trust that your analysis is precise. They say, probably the program is incorrect. So what you want to do is to refine the program so that it meets its specification, keeping the analysis. It's just changing the variables. Okay. It's similar to program synthesis, but slightly different because you already have the program. And actually, there have been a lot of research, or still it's ongoing research, the one of repairing the program starting from test. I think someone knows in the audience. So, and the idea is this: it's you have your program, you have a test suite, and then some tests they fail, and one test they pass, one test fails. Now, what you want to do is just to do a program transformation so that all your tests succeed. That's what the abstract level what they try to do. Which is interesting, but yes, the drawback that in order to do this stuff, you needed to run the program. And our goal is to do it while you are writing the program, or in particular also when you are developing libraries. So you don't really have a test case yet or other things. So the program can even, for instance, cannot even compile because it can be incomplete. So that's one problem, is that we cannot run the program for anything. And the second one is that it does not really have a specification. So a specification is as good as the test suite. I think one of the first papers published in this area of research, they were fixing assertee by adding an if-he assertee. So essentially, they were skipping the assert if was fed, and it worked. Okay, if their test suite was not depending on it, they were just happy. That's a way of fixing a program. So we propose a semantic notion of repair. So we're supposed to have this function R from programs to programs. And intuitively, what this repair should do should reduce the bad runs. We should have less bad runs when we run the program, and should increase the good runs of the program. So we want more assertions satisfied, but we don't want to falsify an assertion I could prove before. And in general, we don't want to remove any good behavior. That's our scope. So I can put a lot of strange Greek symbols here, but I decided to put some English to explain how we can formalize all these things. And essentially, the idea is this, is that we take the program P, and we take the repaired program P. And we take its semantics, which is a set of traces. There are all the runs. There are some good runs, some bad runs. And now we want to compare the two. We cannot compare the two directly, because they can be completely arbitrary, so there will be only trivial repairs that we can enable. What we want to do is just to compare to some level of abstraction. So we want just to see something about those runs, and we only want to compare that some property of these runs are observed. So the abstraction that we have, actually there are 4 abstractions. I just made one because the composition of abstraction is an abstraction. So the first one, what it does is it takes the program and the repaired program, takes the semantics, and now it removes all the states, but those that contain assertions. So we only wanted to observe assertions, only things that can be violated. So assignments, other things, we don't care. Just we want to see the states where we have assertion. Then we remove all the assertion in the repaired program, which they don't appear in the previous program. Because when I essentially change my program, I repaired it automatically. I may add a new piece of code, and this piece of code, for instance, can have new access to arrays or to the heap. So there can be new assertion. We are not really interested in this assertion. So we remove this assertion. We just want to repair the old assertion. And then we don't really care. So I say that our runs are a set of traces, so there is an order among it. I don't really care about the order. I only care about the assertion. So we abstract from traces to set of states. And eventually, I'm not really interested about the values at this program point in the assert, but I'm only interested if the assertion it holds or not. And so composing this 4 abstraction, essentially I get my abstraction. That's what I want to do. I want to just say, okay, whenever I get good runs in a good program and I get all these abstractions, so I see only the assertion that holds in the good runs, where they should still hold this assertion in the good runs of the repaired programs. But also I wanted to have fewer bad runs when I see this thing in the repaired programs. So it should be smaller than that. So that's the definition. So that at least gives us a way, to fix a program. Otherwise, we can just fix a program by just putting assume false or other things, never call me. Or just put skip, never get an error. Now, how these things works? Now, the idea and the key insight is that actually, when we do the analysis and we have these little boxes we saw before, actually we know a lot about the program. So here it's the most trivial example I can think of, or repairs, which is not so trivial to the programmer. It's kind of, we use too many trivials in this statement. So there is a problem in this program. So you take two doubles, you sum them, you write this into a field, and then you check if the field is equal to TMP. I know, yeah, usually textbooks say don't do equality among doubles, but here it seems that you can do the equality among doubles because it's exactly the same thing, isn't it? So this thing should always be true. Isn't true? And actually, it's not the case. It's not the case in .NET, and it has to do with something about the architecture of x86 machines. Oopsie, sorry. So because this is a double, so it's a 64-bit. But actually, it's a parameter, so it's a local. So in .NET, say that you have to use the highest precision possible, which is 80 bits on an x86 machine. So this is 80 bits. This is 80 bits. Now we do 80 bits plus 80 bits. The result, it goes into a local, so it's 80 bits. And now, when you have this local, you write into a field. The semantic of .NET says that now you have to cast to the nominal type, to the precision of the nominal type. As f is defined to be a float 64, now you take this 80 bits, and so the runtime truncates to 64 bits. So here you are comparing two different quantities, because this is it's 80, truncate 64, read again in the register, so it gets padded with zeros. Yes?
This is only true if you're running on an 8087, the old version of the CPU, which Intel have now downgraded.
Actually, unfortunately, this is true also on ARM processor and many others. I can take it off. Even ARM and other processor, it's okay. I have a whole talk about it, but yes, unfortunately, it's something has to do with performance and design. Yes.
The new newer Pentiums don't have this type of. They have two floating point instruction sets. Indeed, we can take it offline. But what I was just going to ask is the result. I mean, I thought in most programming languages, when I add two integers together, I get an integer. When I add two doubles together, I get a double. Are you saying that in F#, when I add two doubles together, I may get a higher precision?
Yes.
And that's part
when they are local. Yes, that's part of the specification. It's written a specification. I went to read it. But actually, it's still true with Pentium. We can take it offline. I run on this machine, which is a Core i7, and it happened. So
but
they didn't fix
it. In GCC with C, where they cheat over this.
I know. Java also is strict or whatever, but that's .NET. So, okay, now the fix here, it's easy, actually. So that was my thing, because this thing is 64 bits. This one is extended precision. So what you want to do is to compare the same precision. So what you have to do is just to force A plus B to be a 64, and the way in which you do it is by adding a cast to double. It's funny, but that's the way in which you do. This is a double, but you cast a double, and it's not identity. That's the way to do. But it's a very unintuitive fix. But that's the way in which you fix the program. So that's what the tool will say. Say, okay, these two things are not the same. I suggest that you put a cast. Or more interesting, you can do it for binary search. So I think you know about the family. Yes? Yeah. It's abstract domain specific. Essentially, the way in which it works, so each abstract domain, you ask, this is the piece of code. Do you know how to fix it? It's the same way in which you ask the abstract domain. Do you know if this is smaller than that? Do you know if this is old? It's just another primitive of the abstract domain. So, yes?
You have the list of possible fixes.
Each abstract domain knows the fixes. So, yes, the list is here. So, and probably this example is a little bit more interesting. So, you know about binary search. You know about the bug with binary search. Yes, I guess assume everyone knows the bug with the binary search, which, they were computing the element in the middle by doing inf plus sup. So what's happening when we give this example to Clousot? Well, Clousot will infer the loop invariant, infer that, the lower bound is more equal than sup which is smaller than the length of the array, which can be equal to 2 at 31 minus 1. And by using this information, it cannot prove that this expression does not overflow. So it will emit a warning about it. And this is going to be annoying because we are going to get a lot of this warning. So what we want to do is not only to give the warning, but also say how to fix it. And in fact, that's what the tool does. It just suggests a repair. Say, instead of writing inf plus sup divided by 2, write inf plus sup minus inf divided by 2. And essentially what the tool is doing in this case, we have these numerical domains. We say, OK, this thing can overflow. Are you able to get me an expression which is equivalent in Z, which does not overflow? And in this case, it comes out with the answer. I say, yes, essentially, it's just doing the rewriting and trying to prove it works. Yes?
You treat all arithmetic overflows as bugs by default? Or
OK, so we have several modalities. So by default, we say when we have assume don't overflow. That's what we do. In the next computation, assume this thing doesn't overflow. We have a flag and say we want to check for the overflows, and now we give you all the overflows. Or we have the default in which we say we only talk about overflows when we know how to fix it. Which so I try to make it. This is the case. You see? You say, okay, in this case we know this guy can overflow. So, but we know how to fix it. So you say replace this with that. So that's. You don't want to flow the programmer with the overflow. Because the problem is that if you want to make it right, then you have to add a lot of contracts, way more they want to write. So it's a trade-off. So we have a switch. You can get all the warnings you want to and get it. And then there are things also because in .NET there is a difference between overflow and then they are checked expression, which they throw if they do overflow. So, and well, we have a list of Step 3. OK, now. We know how to check things. We know how to repair things, at least for some classes. Is it enough? Actually, a big part of what I did in last year is can we infer contracts? How we can infer contracts? Because ideally, the programmer just goes there and provides all the specification, all the boundary specification, the precondition, the postcondition, as it does for types. That's the ideal setting. But actually, it turns out that no one is ever going to do it. Because the feedback you get is, OK, I have a method, I return a new A. It's new, so I know I'm returning something which is not null. Why should I write it? That's the argument. And for many other things, yes, they say, oh, why is not inferring it? It's just evident. Or I want only to add the contracts I'm really interested in. The one only makes sense. You know, the other things are evident from the code. And the definition of evident, it's very hard. And the problem is that you know, they have this first approach, this first thing. So they take the tool, they run it, they start tweaking, say, oh, why didn't improve it? It's a dumb tool. And then you're done. You screw up when they get this thing. So we need the tool to help the programmer. So you know, so we need to be smart. We need to infer as many dumb things and evident things as possible. Now, in the following, it's important to make clear the distinction. I think here everyone knows logic, so this should be very, very easy. But distinction between sufficient and necessary. So if I have a formula, S implies N, S is sufficient for the condition N, and N is necessary for the condition S. And for programs, essentially what it means is that the condition S is sufficient. If it holds, then the program is correct. Similarly, if N is necessary, in that if it does not hold, then P is incorrect. Easy. Now, why this is important? Because say we want to infer contracts, and the first contracts we want to infer, for instance, are preconditions, usually. Those are somehow the most important, the one that programmers see more important. And after thinking a lot, and I give examples, turns out that when we do automatic inference, the only precondition makes sense to infer for the user to do it automatically is a necessary precondition and not a sufficient. And intuitively, it's because of this. Because a sufficient precondition, they say, if this holds, then my program is correct. But they can be too strong because you have loops and other things you don't know in the program. So what you are going to do in general is you are going to under-approximate it. Now this thing gets propagated to the caller. And now this caller should prove something which is harder what really in reality is, which he has in the concrete semantics. And people will be unhappy with it. Whereas a necessary precondition is something that say this should hold, otherwise you will get an error. So checking this thing here, or the precondition or the call site, it always makes sense. It's always a condition to error somehow. Let me show you with an example. It's a very simple example, but actually this came, it's a real example someone posted on our forum, outside the company forum. And they were unhappy. Why? So this code, what it's doing, it just say if x is greater than 0, return the reference A, essentially. Now, the necessary sufficient precondition in this case is that either x is more than 0, so the reference A will go there, or if it is greater than 0, then A should be null. So this is the one. And at the beginning of the time, we had some inference algorithm was doing sufficient condition, and this tool was saying, okay, I'm inferring that A should be different from null, because you may say, okay, I don't want A to be null. Now, the problem comes that programmers, they can call this example by, this function example by putting -2 null. And the program is correct, but our tool say, oh, the precondition is false, because I ask you A not to be null, you're passing null, that's false, and then everything scrap. And then people were unhappy with it, and that's, I quote, they called it a wrong precondition. They were unhappy. So in general, it's hard to infer sufficient and necessary precondition. The problem is usual. It's because of the loops. And if we want to sufficient, we have to under-approximate, whereas necessary, we can over-approximate, so still be safe. And we have several algorithms for doing this inference on necessary conditions in Clousot. And here I'm just presenting a schematic approach for this simple piece of code. So we have first one is the all path. It's very simple. And the idea is this. If I have some assertion which is checked in all the path inside my method, and this assertion is something that is not modified from the caller, so it just depends on the state at the entry, then this should be an assertion. Should be a precondition. So, for instance, in this case, no matter what I do, I'm going to hit the loop. Oops. The loop head, and the loop head is that A should be not null. And so this is definitely a precondition that I want to have. It's necessary, because I know if A is equal to null, then the program will crash. But it's not sufficient, because the program can be still incorrect. Then we have a more sophisticated one, in which we do essentially backward analysis, doing dual widenings for people like outside interpretation and these things. It's kind of exciting concept. And in this particular case, we infer that the A dot length should be greater than 0 with this analysis. Well, actually, we also infer that A is different from null, but I just wanted to simplify things. So if we go here, we get I equal to 0, and the first iteration, we get with the reference, we access A of 0. So we should have at least one element in the array. And if we continue with iteration, say, okay, if the first element is not 3, then it should happen that we have at least 2 elements. And if the first and the second element is are not 3, then we should have at least 3 elements, and so on. And also, we have a different static analysis, which is kind of cool. Yeah, probably I should not say that it's cool, because I did it, but I found it cool. So in which we can also infer the existential one. We say that, okay, this program, I reached this program point if exists a value such that A over J is equal to 3. So there are different degrees of inference of precondition we can do on necessary precondition here. How it looks this, for the programmer? Well, it looks like that. So this example is very similar to the one I showed 2 slides ago. And why it goes? Oh, tip. So this one is quite similar. So what it is inferring is that x is more than 0 or p different from null. Okay, now I have a question for you. Why we use this symbol or instead of implication? Why we may not have a contract that implies? It's just to wake you up so I can drink water. The question is why the tool infers x smaller than 0 or p different from null instead of inferring something as contract requires contract dot implies x smaller or equal than 0, comma, p different from null. Well, we have contract dot, so we can just. Yeah. What? Yes.
X may be undefined.
Yeah, it's the problem came on the fact that in C#, evaluation of parameters it's eager, whereas the or, in a way, it's lazy. So that's the problem it came. It's about lazy evaluation things. And okay, so we infer this one. And then we propagated this program point here. And now we are passing 1s. So we know that 1 is more than 0. So this is true. 1 is more than 0. It's false, sorry. So this goes away. So p different from s, from null, but p is s. So we infer for call infer not null, s different from null. It requires s different from null. So this one. And now we call it with null, and we emit requires it's false. And we give the trace to the error. We say, OK, you do this, and then this, and that. So, yes?
Is the double bracketing of the or meaningful?
No, it's just it's an error in the pretty printing. I take all the shame for it. Sorry. Yeah, it's probably fixed since then, but yeah, it's a nope. And the ideas for the inference of precondition can also be generalized for the inference of object invariance. I have this simple read-only example. So I have a read-only field. So a read-only field in C# is a field that you can only assign in the constructor. Almost. You can change with serialization, but we don't do serialization. Let's say all meaningful C# you can only change in the C# in the constructor. Oopsie. Okay, sorry. So we assign this my field, and then we have this divide. We just take t and we divide by this my field. So now there is a problem because here we may have a division by 0. We don't know anything. This thing can be 0. So, but we know this is a read-only. So what the tool is doing is say, okay, this is a necessary object invariant because otherwise you can construct this object by passing 0, and then you call divide, and then you get in trouble. So that's why the tool now is suggested the invariant that this my field should be different from 0. That's one thing. And now that he has this precondition, this object invariant, now it turns out that also we are not allowed to assign my field a value which is equal to 0. So now we generate a precondition and say that x cannot be 0. So essentially we are propagating it. What we are doing a fixed point. Actually, it's a greatest fixed point if you like this thing. So we are doing least fixed point, a greatest fixed point or least fixed point. It's very exciting. And it's great. More than cycling, imagine. And then we still get a warning. Now we get a warning here. So, and say that we may have a division, we can have an overflow. So again, for this overflow, we always say about these overflows because they're important. The people, they don't think about it. And you get an overflow because you're dividing mean value by -1. So you get an overflow. And we are not generating anything for it. So why we are not generating a precondition? This is one of the cases, the tool does nice things, but it's not magic. And
there are two clear fixes, and neither one is clearly better than the other.
Yeah, that's one thing. And in general, our inference, it's always we will never remove good runs. Whenever there's a good run, we keep it. We never want to make the programmer crazy because say, oh, you removed this crazy behavior that I wanted. We never do it. We always are safe. We always remove things that go badly. Now, the problem is how we can fix this thing now. We can add a precondition. But which precondition you want to put? We can put a precondition at t is not t is not mean value. Why should you? You want to divide the mean value by 1. The problem is when both mean value and my field, when t and my field have this particular point. Yes? Sorry?
Can the preconditions be relational?
Yes.
So can you not correlate my field with t?
Exactly, but that's actually, I should have put it. Actually, the tool will find this thing, but it's not a precondition. And the problem is because my field is private. Now you cannot ask to the caller to have this precondition. You cannot say okay, you have to have this relation among the thing you are passing me and this thing is private to me. It's very unfair. You cannot ask it. So the tool will discover this property, and it does not. Actually, what it will suggest is to put an assume. And just say, okay, believe in this program, this is what's happening. But yeah. So those are tricky things when you go and start reasoning with contracts.
What you're trying to say is when you call the constructor and when you call the public interface, the two values weren't in a relationship, but it's not obvious how to encode that in a system.
In general, it's very tricky because well, actually the tool, what it's going to do is going to infer a postcondition for you saying, whatever you pass me here, it's equal to a value of my field. And then, but here it does not have really a way to reasoning it. It's something, actually this is a problem with the specification language somehow. There is something with commonality. So there are limits. So what I say is we trade some beauty and some expressiveness for being effective. So here, essentially, you get the warning, and now the programmer should change the code as he wants, or she wants.
With the precondition, postcondition mechanism.
Yeah, it's the problem with the subtyping behavior, essentially. Behavioral subtyping and what is visible and what is not. That's very different. And eventually, all this machinery can be used for the inference of postconditions. So something when often you get warnings and problems is this one. It's because you get some interface, and then you call something about this interface, and you use the value, and for instance, you want x not to be null, and then you are in trouble. And what the tool does here says, okay, look, here I expect x to be not null, and this x came from this guy, and this guy, it's an interface, so now it's better you put a postcondition to this interface method so that you are sure that all the implementation of this interface will satisfy it. So it's the same thing. Step 4. Still, we have a lot of steps, and I think it's more or less is plus infinity, but I have a finite amount of time. So probably I'll do this one, and then Alrighty, so that's a recent result, or even if probably Shuvendo talk a little bit about it when he came here. So it's now the problem. Another problem you have all these nice things, for checking and inferring and verifying, and everything is beautiful, except that you go and take your code base which has no contract, you run Clousot, you get a lot of warnings, even with the inference. That's another bad thing. So why this happens? Essentially, this happens because real code bases, they start referencing things that we don't know, for which we don't have contracts. So the tool makes over approximations. Just say, what is this library? I have no idea what it's doing. So you can do everything, and then it gives a warning out of it. And you can go instrument it. And actually, we have a way. That's some other thing I'm not talking today. We did with my intern, Scott Kerr, for instrumenting this thing. So this is kind of orthogonal. It's to infer these contracts and then add them automatically into the code, but that's like this. And the general solution, which all static analysis, commercial static analysis do, is to baseline the result. Essentially, they say, okay, this is all the warnings that came out. So here I have some piece of code which read the temperature in Celsius. It converts into Kelvin and returns the value. And now we know from basic physics that Kelvin can never be negative. So this assertion is always true, but I think there is no static analysis in the world that can prove it. Unless it's made by physicists, I don't know. And so we get this assertion. We say, okay, no problem. What you're going to do is, so that's with synthetic baselining. You just take the assertion on line 3, and you just mask. Next time you analyze the program, here I change the code. No, here it's, yes, here I change the code a little bit. You say, okay, this is fine. Just don't show the warning. Now the problem is that what happens if I introduce an error? So, for instance, if I change the constant, the absolute value of the constant for the absolute 0, absolute, how many absolute? So the program now is incorrect. But by masking the thing at line 3, I will not show this warning. And this is bad. This is a warning I want to see because this is a regression. Or similarly, if I change the code a little bit, now I say, I wanted to round my value, let's say having only two digits after the comma. Now, as I'm baselining at line 3, well, I'm not showing whatever precondition or whatever assertion I have here, but I'm resurrecting this one. But this is correct. I don't want to show this one. This assertion is still correct if it was correct the previous one. Yep.
You have rounded down?
Yeah. Okay. Yes. You are right. Yes. It can be with floating point. Awful things can happen. You are right. Yeah. I try to have the simplest example make sense. Now, Well, yeah, is this a straw man? Yes, I made a simple example, and the schema for the baseline, it's really trivial because it just takes the line number and things move, shifts, so does not work. Yes, that's a very simple example. But what I want to say is that in general, synthetic schema, they are really brittle. You can break easily, and they don't provide you any semantic guarantee on the things they show you and the things they don't show you. So the idea with the VMV, verification modulo version, is take a base version of your program and extract this correctness condition on the external world, on the external input, and then save somewhere. Now you have your new program, and when you analyze your new program, you just take this condition, you take the old program, you instrument it, so you construct this instrumented program, and now you analyze this program. And now what I claim is that you have semantic guarantees on it. So how it works in this example? Well, here again, it's clear that this program is correct if and only if the value returned by read temperature is larger or equal than the absolute 0. So we are going to save this thing into the database. We remember that this code, the previous version was correct if and only if that condition hold on this external API, which I have no idea what it's doing. Now, if I change my program and instead of having 15 and now I have 0, by adding the assumption we had before, we are no more able to prove this assertion. And now we report a warning, because now essentially you need a stronger assumption you needed before. So we call it a regression now because you are asking more to the same API than before. Or on the other hand, up to the rounding errors on this problem, where you round it, right? Now, when we have the problem with round, well, using this assumption, now we are able to prove this thing. So we say this is not verification, it's relative verification. It's with the assumption I told in the good runs before, I can still prove it. So it's a weaker notion of verification. And yeah, that's essentially what we do in one slide. And things get tricky because now we have to talk about when you extract condition. Again, I think you understood from the talk that it's important to reason if this is sufficient or necessary. So that's very important, the very first point. Then when you instrument it, actually is where you're going to insert this assumption. This is another tricky point that gives different results and different precision levels. And third one is without the semantic guarantees. So very sketchy. If what you infer is sufficient, then you have bug finding. It is all the warnings that are shown to you are new warnings, so you want better look at it. But you don't know anything about what is not shown to you. And dually, if they are necessary, now this is for relative verification. Everything that is proven, it's either proven because it's true or proven because you are using the assumption of the previous program. But we have a warning, you don't really know. This can be an old warning or a new one. So that's it. And I think I skipped step 5. I'm sorry, I think I'm running out of time. So. I was sorry because there was this nice thing. These abstract Hoare triples. And there was this counterexample. Okay, but I have no time, sorry. But I really loved this idea of abstract Hoare triples in front of Hoare. So. And well, very quickly, the idea, I can just give the idea of what is the idea. It's that another problem that comes is that the program, they change. They get modified, they get refactoring. And so we had the program, we had the proof. Now, you change the program somehow, you cannot prove it anymore. So we want also to have this form of proof-preserving refactoring, so that when you change the program, we also generate contracts, pre- and post-conditions, so that the proof still goes on. So and we have something for doing something on this. So the conclusions, and try just to sum up. We have 3 minutes left. Essentially, yeah, my goal is to have this. To bring in, verification to the working programmer. Just make, don't need a PhD in order to use verification to get all the nice things that we do in academia, all nice tools that we have. So, and for doing it, we need the verification to be user-friendly. We have really, when we go and design our tools, to think at the user before that to ourselves. So I think that's very important. I always think that what we need is that the tool should use the programmer, not the programmer should help the tool. That's maybe. We need it to be precise enough not to generate stupid warnings, not to be called dumb. I already heard this thing. And it should scale up because the real code out there, it's big, it's large, there's a lot of code, and every day gets produced more and more and more code. And we need to be as automatic as possible for inference and other things. So my little slice in all this vision, I contributed to the CodeContracts project by having this library to specify contracts and using abstract interpretation in order to verify things, because so we can be more automatic, we can be deterministic, which is important. We can focus on properties which matter most, so we don't aim at full functional correctness, but still things that make sense. And in order to do this, there are several steps. We need to infer contracts, we need to be able to repair program, and then to give fewer warnings, still giving semantic guarantees, and also help in refactoring. Again, 1 minute left. Okay. Thank you.